Number 20. Simplify the radical expression. So the key idea is the power inside the radicand should be less than the index. So let's do them one by one. So for part A, first step should be factorize your number, or say the coefficient in the front using only prime numbers. So 8, you should factor that as 2 times 4, and 4 is not prime number, so again that should be 2 times 2. So it will be 2 times 2 times 2, so 2 to the raised to the power of 3. So that's how to factor the number, or say the coefficient part. Then we want to give this index to each one of those exponential expression inside. So 2 raised to the power of 3 over 3, m raised to the power of 3 over 3, n raised to the power of 7 over 3. So basically you give the power of 1/3 to each one of those exponential expression. Then we want to look at them, those 3 parts. So for 2 raised to the power of 3 over 3, because 3 over 3 is just a 1, so 2 raised to the power of 1, so that's just a 2. For the second part, it's the same, so m raised to the power of 1. That's pretty good. For the third part, because this power is 7 over 3, this is not an integer. What we want to do is using that countdown method. So if we count from 7 down, and we want to find the first integer that is a multiple of 3. So 7, which is not a multiple of 3, 6 it is. So we can stop here. We can rewrite this 7 as 6 plus 1. So that this fraction, or say this power here, we can rewrite that as 6 over 3 plus 1/3. So it will be n raised to the power of 6 over 3 times n raised to the power of 1/3. 6 over 3 is good because it's integer 2. So in the front, we will have 2mn raised to the power of 2, and then n raised to the power of 1/3, which is exactly the cube root of n. This is a simplified version of this initial expression. So part B, we use very similar process. First, we need to factorize 24, the coefficient in the front. So that will be 3 times 2 times 2 times 2. So if you factorize 24, you can see that immediately. And then we want to give the power 1 over 2 to each one of those item inside. So 3 raised to the power of half times 2 raised to the power of 3 over 2. And for remaining part, each one of them will have a power 1 over 2 multiplied for the power. Then we want to look at each term. 3 raised to the power of 1 over 2, there's nothing much we could do for that. And then for the 2, it's power 3 over 2. 3 is not a multiple of 2. So we use the countdown method. We count from 3, then 2. 2 is good because 2 is a multiple of 2. So we rewrite this 3 as 2 plus 1. And for the next part, x has a power of 5 over 2. Again, 5 is not a multiple of 2. So we use a countdown method. 5, then 4. 4 is good because 4 is a multiple of 2. So we rewrite this 5 as 4 plus 1. Then for the y part, y has a power of 12 over 2. This is good enough already because 12 is a multiple of 2. So 12 over 2 is 6. We can rewrite this. And for the z, its power is already pretty good, so we just copy that. And then we want to rewrite for the 2 and the x part, we will rewrite that as the 2 parts. So for the 2, it first raised to the power of 2 over 2, which is 1. So it's just a 2, times 2 raised to the power of a half, times x raised to the power of 4 over 2, which is just a 2. And then x to the power of a half. For the remaining part, we just copy that. And then we want to find all those exponential expressions with integer power. Put them on the left. And then for all the other remaining part, we will put it on the right. So that will become the square root part. And we will write them as a big square root. So that will be 3 times 2 times x times z in the radicand. And one more step, 3 times 2 is 6. So that's our final result. Part C, very similarly. First, we deal with this coefficient 40 in the front. We rewrite that as a bunch of prime numbers multiplied together. So that will become, 40 will become 5 times 8. And 8 again is 2 times 2 times 2. So 40 will become 5 times 2 raised to the power of 3. Then we give the power 1/3 to each one of those factors inside. So 5 raised to the power. 5 raised to the power of a third times 2 raised to the power of 3 over 3. A raised to the power of 6 over 3, and B have the power of 10 over 3. And we look at each term carefully. For the first one, there's nothing much we could do, so we'll just put it here. For the 2, the power is 3 over 3, which is just 1. So, times 2. For the A part, it's 6 over 3 for the power, which is 2. So A squared here. For the B part, it has a power of 10 over 3. 10 is not a multiple of 3, so we count down. We can see that 9 is a multiple of 3. So B raised to the power of 9 plus 1 over 3. We can rewrite that as, so for the first 3 parts, it's the same. And for the B, it will be have the power of 9 over 3, which is 3, and times B raised to the power of 1 over 3. And we know that this part in the middle has has all the integer power. So it will be put to the left. And for the remaining part, this and that, we should put it on the right. So this will become the cube root part. So one more step. So we put this 5 times b in the radicand. So that should be the final result. Question 21. State the domain for each of the function. So we know that for the square root, we need the radicand to be bigger or equal to 0. So for part A, x plus 3 is bigger or equal to 0. So x is bigger or equal to negative 3. That should be your domain for part A. For part B, very similarly, the radicand x minus 4 is bigger or equal to 0. So x is bigger or equal to 4. That is your domain for part B. So that's question 21. 22. Find x such that fx equal to 0. So for part A, you set the right part equal to 0. So 2 times this square root minus 6 equal to 0. You add 6 on both sides. So 2 times the square root equal to 6. Divide by 2 on both sides. The square root of x plus 3 equal to 3. So then you square on both sides. So x plus 3 will be 3 squares, which is 9. So x will be 6. One thing you need to pay attention is for the radical equation, you have to be careful about the extraneous solution. That means the solution you get from solving your problem, but it is not a solution for your original equation. So what you really have to do is plug in your solution into your original equation, just to make sure it is indeed a solution there. So you plug in x equal to 6. So f of 6 is 2 times the square root of 6 plus 3 minus 6. And if you keep calculating that, is 2 times square root of 9, which is 3, minus 6. So 2 times 3 minus 6, which is indeed 0. So that means x equal to 6 is indeed a solution of your original equation. That is good. That means x equal to 6 is a solution. Part B, we do very similar things. We set right part equal to 0, minus 8 on both sides. So 2 times the square root equal to minus 6. Divide by 2 on both sides. So the square root will be minus 4. Square on both sides. X minus 4 will be 16. And x will be 20. So again, we need to check whether this x equal to 20 will be the solution of the original equation. If we plug in x equal to 20, the right part of the equation, the function will be 8 plus 2 times the square root of 20 over 4, 20 minus 4, which is 16. So 2 times 16, square root of 16, which is 4, will be 8. So 8 plus 2 times 4, which is 8, is 16, which is not 0. What you want to solve is fx equal to 0. But this one, if you plug in x equal to 20, that makes your function not equal to 0. That means x equal to 20 is not a solution, it's extraneous solution. If you look at this step, you may already see that there is no solution for this fx equal to 0. Because the square root is negative 4. Square root cannot be negative. So for this one, there is no solution for x. But for other equations, you may not see that clearly. So that's why you always need to check by plugging in your solution into original equation. So it's necessary.